Hey, good morning. This is a session of defect prediction and defect detection and prediction. My name is Wei Le. I am the session chair. We will have 6 talks, 15 minutes each, technical talks.
Hello, everyone. Today, I will show our work on detecting exception handling bugs in C++ programs. I am the speaker. My name is Zhang, and I'm also one of the authors. Here is the full list of all the authors. So let's start. Studies have shown that the exception handling code is error-prone. However, there is still a limited research on detecting exception handling bugs, or we call them EH bugs. So what is an EH bug? Actually, any bugs that are related to exception handling can be called EH bugs. In our work, we only focus on EH bugs that happen when there are exceptions being thrown. Let's see an example. There is an example of memory leak. The variable x will be leaked if bad function throws an exception. This is a very simple example and is also typical. We have tried several static analysis tools on this example. Some of you might be familiar with these tools. However, none of them detected such memory leak. This is because they do not properly model the exception behavior. What is our approach to detect such EH bugs? Our technique is based on static symbolic execution. First, we extend a CFG, the control flow graph, so that it can show the exception control flows. Secondly, we extend the classic symbolic execution so that it tracks the exceptions. The extended CFG can precisely present the exception handling and stack unwinding. More specifically, it consists of control flows when exceptions are being thrown. We extend the classic symbolic execution mainly on the program state. We use a stack gamma to track the exceptions. I am not going to talk the technical details here. Instead, I'd like to use 2 examples to show how we extend a CFG and how we track the exceptions. So now let's just move on. We have implemented a tool called EHA on top of Clown Static Analyzer. The tool is open source and you can find it on GitHub. Most important, how good is our tool at detecting EH bugs? We evaluated our tool in 3 aspects. First, how does EHA perform on real-world projects? We have found 36 bugs in 8 popular projects from GitHub. Among them, 20 were confirmed by the developers. On these projects, EHA has a precision of around 84%. Second, how does EHA compare with other analysis tools? We compared EHA with other tools on a handmade benchmark. We made this benchmark by randomly injecting EH bugs into these projects. In the table, P stands for precision and R stands for recall. We can see that our tool has a relatively high precision and a very high recall compared to other tools. Third, how does EHA improve the original Clown Static Analyzer? our tool is about 9% slower than the original CSA. However, it explores 25% more paths. Besides, 24% more paths are exception paths, which are not and cannot be explored by the original CSA. Next, I will use two examples to show how we extend a CFG and how we track the exceptions. On the right side, there is a simple piece of code. On the left side is the control flow graph. S stands for statement, and D represents the destruction. For example, S1 refers to the first statement, and D1 refers to the destruction of object created at S1. We first split the block at S1. Then we figure out where to go if S1 throws an exception. The red line is called exception control flow. We then split at S2, and again we build the exception control flow, which is from S2 to D1 and from D1 to the exit block. Next, we split at S3 and build the control flow, which is from S3 to D1. Note that the control flow from D1 to exit is already existed, so we just stop at here. Finally, we split at S4 and build the exception control flows, which is from S4 to D3 and from D3 to D1. After building the exception control flows, we then merge the blocks. Some blocks have exception control flows pointing to the same block. These blocks can be merged, as shown in the slide. The two blue blocks can be merged, as well as the two green blocks. And this is the final extended control flow graph. This CFG will then be used by the symbolic execution. This is how we extend a CFG. Next, I will use another new example to show how we track the exceptions. On the right side, there is a little complicated program. We will use this example to show how we track the exceptions with the help of the stack gamma. At the beginning, gamma is empty. After the statement throw 1, there is an exception, which is int 1 in the stack. After statement throw 2, the exception int 1 is popped out because it can no longer be referenced and we do not need to track it anymore. And another new exception, which is int 2, is then pushed on the stack. After statement throw 3, another new exception, which is int 3, is then pushed onto the stack. Now there are 2 exceptions in the stack. After throw 4, both int 2 and int 3 are popped out because they can no longer be referenced. And a new exception again, the int 4 is then pushed onto the stack. So at the end, we can know that there is an exception of int 4 being thrown out of this example function. And this is how we track the exceptions. At the end of my presentation, I want to show some bug reports and fixes. There is not much time left, so we just have a quick look. This is a memory leak. The black box is the bug report, and the blue box is the fix. It is found in my SQL server. This is an initialized variable. The exception is thrown, and which causes a variable uninitialized. The last one is, again, a memory leak. The developer fixed this issue by replacing the raw pointers by smart pointers. Thank you very much. It's now question time.
How did we generate the CFG? Is there any tool, open source tool, to generate the CFG at the very initial step?
Okay, the CFG is, actually our tool is based on Clown Static Analyzer, and the CFG is generated by Clown. The original CFG is generated by Clown, and we extended the CFG.
So Cloud is the open source tool we can use to generate CFG, is that right?
Yes.
Can you show the slide of the after merge slide? I was wondering, why do you have two different exception nodes? Like you have after merge, you have a D1 and D3, right? For the exception flow. Why do you keep the two different flows? Because you can just indeed merge them.
If any statement in the merge block throws an exception, the control flow goes to the block which is pointed by the red line. If these blocks are same, they can be merged.
I mean, my point is that currently you don't have a try-catch block here. So indeed, the exception flow from the statement 4 and statement 3, they go to the same flow because there is no catch clause here. If there is catch clause, you have to split them, but in this case, you don't have it.
No, there is actually the distractions. Because if the statement 3 throws an exception, the control flow should first distract the object created at S1. If statement 4 throws an exception, the control flow should first distract the object created at S3. So they cannot be merged because they have different paths when the exception throws.
I was wondering whether you're planning on contributing the work upstream to Clang, or whether it's going to continue as a separate project.
The tool itself is built on top of Clang. However, this control flow graph can be used for example, for data flow analysis. Although we just use this control flow for simple execution, if someone might want to use data flow, this control flow might be helpful, I think.
Thank you.
I have a quick question. So there's a Java exception flow papers in the past. So what C language bring its own challenge?
The challenge is most on the distractions. In Java, actually, there is no such things. We do not need to care the distractions. Actually, there are previous works on C and C++. These works, they do not consider the distractions, just like Java. These works are not suitable for the real-world projects because in the real-world project, there are lots of class objects which relies on the distractions.
Thank you. Let's thank speaker one more time, then we move to the second time.
Okay. Thank you. Thank you very much.
Okay, hello everyone. My name is Yoonseok. I'm a software engineer at Meta, and the title of this talk is Learning to Boost Disjunctive Static Bug Finders. This motivating example is taken from the open source project BlueZ. So let's assume that before these two lines of code, let's assume that we have a variable REC, which has which points to some kind of object that has a property ATTR list, and ATTR list points to some kind of linked list. In this example, the linked list element is just only one. First function called SDPSEQ it allocates a new memory block and returns the address. So now P points to some kind of a memory block. Second function call has 3 steps. The first one is allocate a new linked list memory block and assign the address of the variable P to its data field. And then insert the memory block into the linked list in REC. So far so good. But if the first step fails, the second function call just return it as it is, which means that at the end of the function scope, because P was a local variable, there is a memory leak. Let's assume that, let's think about the alarm reporting. And in case of path insensitive analysis result, it would say that somewhere else, some other function, there was a malloc, and then it say that at the end of the function, there is a memory leak, all of a sudden. So developers, it is quite difficult to understand them, and they mostly consider it as a false alarm. And if you consider the path sensitive analysis, it is same, like somewhere else. They say that the memory block is allocated here, but it explains how this value flows to here, and then it is assigned to the variable P. And also in the second function, it also explains the buggy program flow. So if malloc fails, it just return null and then do nothing. So at the end, memory is leaked here, and then developers can easily follow and understand what is a memory leak. So path sensitivity is essential for precise and explainable bug report, and this is quite crucial for in the industrial settings. But the challenge here is that it's well-known path explosion problem. I explained that first function call was quite simply just allocate the memory block, but indeed it involves 6 different function calls and resulting in over 1,000 different execution paths. And the second function call is worse. It has like 8 different function calls and resulting in over 2,000 different execution paths. So in the end, we may have to consider like millions of different execution paths. So analyzing its path separately is not scalable at all. In case of infer, they use a state selection heuristic. So it maintains only k number of states at a time. So for example, let's say case 3, and also assume that before this if branch, we have a 2 pre-states, y is 3 or y is 4. Then for each state, depending on the value of C, it may have true or false, so that it will produce 4 different states. Because infer only maintains k number of states, like a 3, so that it just selects 3 of them and discard all the others. By this, it improved the precision, but this selection heuristic significantly impact on the analysis result. And also, it is quite challenging to devise it manually because we have to consider the state and program context and then also program syntax. So our method is quite simple. Let's learn a state selection heuristic from data. So the code that I've shown, if you use original infer with K20, they do not report this memory leak. But if you use a data-driven infer with K5, report this memory leak. So this graph shows the efficiency of our approach. So if you see the original infer, the analysis time of the original infer increases exponentially after it discovers like 1,400 alarms. But in case of data-driven infer, it does not have this issue. Overview of our approach is like this. First, we train multiple programs as a training data, and then we produce multiple models. And then actual analysis stage, in order to analyze the target program, we use those M candidate models and then produce an alarm report. Here are those two challenges. There are two challenges. The first one is it is challenging to collect a sufficient amount of training data, and the second one is there is no universal model that fits all programs. I will talk about the first challenge and how do we address that. So we propose some efficient trace collection algorithm. Trace collection algorithm is like this. We have a given static analysis that produces a set of reachable states. And we extend it to trace augmented analysis, which produces a set of traces This extension is quite trivial because we just need to put the, connect those reachable states as a line. And for the training data, we analyze those training data, training programs, and produce alarm triggering and non-alarm triggering traces. Here, alarm triggering trace means that the trace that we actually report some bug. But as you can expect that, this trace augmented analysis is much heavier than the original analysis, so that we have to use like a smaller K than usual. Then what happens is that in practice, it's quite hard to collect a sufficient number of alarm triggering traces. So our approach is that is like this. The first, we use a random selection heuristic. So we produce some amount of alarms, and then alarm triggering traces, and then we use this data and then learn from this data, and then we produce some adaptive selection heuristic. And then we use this heuristic and then analyze the program again and again. So in this way, we can easily collect some amount of traces, but the problem is that it rapidly converges and converges into some kind of some specific set of traces, which demonstrates consistent characteristics. So we also use a device repetition avoidance heuristic, which eliminates the repetition in trace collection. So now each iteration produces new traces. So after several iterations, we merge all those traces and then use it as a training data. This graph shows the efficiency of our trace collection algorithm. So compared to random, it collects more traces more efficiently. And next is adaptive model selection. Now we have a training data, and then we use off-the-shelf classification algorithm, such as like a gradient boosting, and then we produce multiple models depending on some parameters. And then we analyze validation set programs with those models, and then we produce some kind of alarm tables. So each model, for each program, depending on model, how many alarms have we found? And then, as you can see that there is no universal model that fits all the programs. So in our case, we propose some kind of adaptive model selection. So first step is offline model selection. After the training, at the end of the training stage, we use this offline model selection and then produce M candidate models. So this table, the left side table is the same. We produce some kind of alarm report tables depending on models. And then let's say we want to select M models. In this example, we use M2. Then all the combination of the two models, we compute maximum number of alarms, which denotes some kind of coverage instead of just summation of the alarms. And then we choose the best combination that covers more number of alarms. And then now we use an online model selection via pre-analysis. This is in the analysis stage. So let's say we have two candidate models, and then we have a target program, and we do some kind of pre-analysis with K-pre, and then produce the number of alarms depending on the model. And then we choose the single best model, and then we analyze the program with the model again. So in this way, we produce the alarm report. This graph shows the efficiency impact of the better model. So compared to the random infer, or compared to the M1, which is just offline model selection, if we spend more time to find the better model, we could have found more alarms. So in conclusion, scaling disjunctive static bug finder is one of the most important challenges in industrial setting. And there are two challenges: how to collect the data and how to apply the trained models. And then we propose two different solutions. So yeah, by employing data-driven technique for learning a state selection heuristic, the performance of real-world static bug finder can be significantly enhanced. Thank you very much.
Okay, good morning everyone. I'm Nicole from the University of Bari, and I'm happy to present our work which is a joint work with the University of Molise, and it's about predicting bugs by monitoring developers during task execution. So, of course, we are in this session, so there's no need to explain the motivation, so why it is important to identify defective part of the source code, and so I will just go to the next topic. And so the state of the art is mostly, so far, state-of-the-art defect prediction techniques are mainly based on, rely on code-based metrics related to the source code or to the process itself. And in many cases, classifiers are actually trained using, for example, supervised machine learning that leverages kind of metrics. So in a recent study, some effort have been made to try to incorporate information about the human aspects. So what actually developers do, their aspect related to their communication, which can be mined, for example, by software repositories and on developer communication traces as well. So in both cases, this kind of metrics depict what developer did. So the feature of the code as well as the action that people are performing on the artifacts. So developers are performing on the artifacts that can be mined from repositories. So our this contribution that I'm presenting today tries to incorporate also another perspective. So how developers perform their development task, and in terms of what is their cognitive and emotional states, where they are fatigued, where they are concentrated, where they are focused, and how this can be measured in terms of operationalized and measured in terms of behavioral metrics that could be integrated in approaches for bug prediction. And this was mostly neglected in recent work, so we were curious to see whether this could contribute to improve classification of the identification of defective code. So the research goal of this paper is to investigate to what extent human aspects can be monitored and measured while programming and can help predicting the introduction of defects in the source code. So in order to address our research question, we have surveyed literature and related work, and we have defined a conceptual framework including behavioral, psychophysical, and control aspects. And behavioral and psychophysical and control factors were operationalized using a set of metrics that they are then incorporated in our bug prediction model. So I will go through each of them. So at the level of behavior, what we observe is the metrics that can describe the high-level activities of developers. So whether they are, for example, focusing on the IDE rather than on the browser. Why it is relevant? Because based on previous work, it seems that this kind of information is useful to understand whether, for example, a developer is experiencing a problem in understanding the problem and the task at hand, whether he needs or she needs to seek for further information, for example, whether a person is navigating the web, or let's say on Stack Overflow because it's searching for an alternative solution to, for example, to develop some methods or some functions. And at the lower level, we also monitor some other kinds of action, which might be an indication of cognitive efforts, such as the scrolling behavior with the mouse, the typing behavior, which can be an indication of the fact that the person is either typing and writing codes, or is actually checking the code when it is he or she is not writing. So this kind of, also the mouse scrolling can be an indication based on previous work. It has been reported that this can be an indication of a lack of visual attention or visual focus. So all these aspects can be useful, for example, in predicting whether a person is focusing on the task or experiencing cognitive difficulties, which could be a factor of risk in terms of introduction of a bug. And at the level of psychophysical dimension, we measure the attention level. We measure some metrics that can be an indication for emotional condition or attention level and fatigue. In particular, we have been asking people before and after the task what kind of emotional condition they were experiencing, whether they were in a positive or a negative mood, and whether they were feeling in control of the situation, which is normally referred as the dominance. And we were also asking people to wear some non-invasive lightweight biometrics, and in particular we use the EEG sensor, which you see here is an helmet, which is capable of recording the electrical activity of the brain, and the wristband, the Empatica E4 wristband, which includes two kinds of sensor. One is for measuring the heart-related activity, so the heart rate, the blood volume pressure, for example, and related metrics, and also the galvanic skin response, which is the amount of electricity conducted by the skin because of sweating. So whenever we experience, anxiety or stress, this kind of parameters varies and indicates that something is happening at the level of the emotional and cognitive cognition. So in particular, GSR has been correlated with stress. So whenever previous work has shown that peaks of cortisol, which is the hormone of stress, positively correlated with peaks of GSR. So it could be an indication that a person is in trouble, for example. So this kind of biometrics can, and also self-reported emotion, can be an indication of specific affective states or mental condition that could impair the, creativity or problem-solving skills, thus inducing better or worse performance while programming. So, and finally, as a control aspect, we are also including information about the general programming experience in terms of years and the specific programming experience with respect to the language which was used during the task, and then the task time before and after the lunch break. So we call this developer-based feature, and we include those in our machine learning experiment to see whether they contribute to the prediction of bug. So the two research questions in particular are, the first one is, developer-based feature allowed to achieve better results compared to code-based features? And also to what extent we can combine both code and developer-based feature to improve the performance of bug prediction models. To answer this question, we designed and implemented a controlled experiment. We involved 20 participants, both students and professional developers. They were required to perform 4 different tasks, and 2 of them were easy, and 2 of them were considered as being hard, and 2 were bug-fixing tasks, and 2 other were implementation tasks. So these tasks were collected from the LeetCode platform, and this was a choice that enabled us to both evaluate the difficulty of the task based on the acceptance rates of the contributed solution, and also to run some tests that were actually able to serve as a gold standard for our machine learning. So whether a code contributed as a solution was considered as buggy or not depended on the fact that these tests were passed or not. And then we also had people developing either during the morning session or the afternoon session. So this could have an impact on fatigue, for example. So this was also included as a control variable. So this is how the data set is composed, which we use for the machine learning. And we have a fairly well-distributed data set, including 60% of buggy code and 40% of clean code. And we did a series of experiments aimed at addressing our research question, and in particular comparing the performance of the code-based model, which we re-implemented from previous work, and all the scripts are available in the replication package in case you want to rerun the study. And also, we also compared the performance of this model with the performance obtained by the model, achieved by the model, which includes developer-based metrics. And we also did all the useful steps like oversampling, feature selection, so more details are in the paper. And we evaluated the approaches using a leave one subject out approach in order to stress a little bit the classifier to see whether what we can learn from n-1 participants could still be useful for the next participant of which we didn't have any data observed. So just to quickly conclude, here are some results. So we can see that the developer-based model actually achieves comparable performance to the code-based one, which is still better performing. And combining both information sources, we can achieve even better performance. And when looking at what are the most predictive features, we found out that the heart rate during the development time, and especially in the last 60 seconds, was particularly useful, and also the typing behavior. So whether a person, both in terms of keystrokes and also the rate of typing, also in combination with the electrodermal activity information and the mouse behavior as well, which is an indication of the cognitive effort, as I was saying earlier. So what kind of implication does this have? This means that this model can be used, for example, while programming to enhance developer awareness of the condition in which they are programming. So maybe prompt them some support messages telling them that they might need a break, for example, in order to avoid introducing bugs. Or maybe that they can recommend doing an extra check of the code before committing and pushing. And so this kind of warnings could be used both for training purposes and for self-awareness, and also to avoid introducing bugs, in the final code which is contributed to the code base. So this is basically it. I hope I stayed in the 10 minutes. So if you have any questions, I'm happy to take them. Thank you.
So I've heard in other forums that there's a stress response graph model, whatever, of too little stress, you also underperform. Did you see any of those effects? Does that factor in here?
Okay, the only thing, I have to say that we have a pool of participants which is made of 20 developers, both students, so it is a little bit hard to generalize, especially because biometrics are very peculiar of each individuals. And in general, yes, stress sometimes can be beneficial in terms of performance improvement, but prolonged stress can be also very detrimental. So this is very personal. We couldn't observe anything very specific to this phenomenon, especially because we were not modeling higher level cognitive or emotional aspects such as stress, but we were just including metrics that could be correlated to stress. So we were not explicitly modeling any specific stress condition to the point that I can answer this question. But what I can say that, for example, one of the worst performing case was one of a subject, and this person was actually showing very stress-like behavior in terms of GSR, but was still contributing a correct solution, which means that either this person is performing better into time pressure or stress condition, which can be the case, or that this person could probably still keep focus and concentration while being stressed for personal reason, for example. So this kind of answers would require some follow-up investigation. So thanks for the question.
What I understand is that when the developer, the heart rate of the developer is high, the possibility to induce the bugs is high. This method might be not stable sometimes. For example, when the body condition of the developers are very good and there don't exist any abnormal situations, maybe your method will not apply suitable for this case.
Yeah, so first of all, I want to say again that, as you can see from the last, oh no, it's not showing, okay, sorry. I thought there was a slide, okay. But anyways, the code-based model, even if we could not implement all the metrics from the work we are using as a reference, was still outperforming the developer-based model. So this can be, of course, regarded as the fact that, this kind of metric is varying from individual to individual and also from condition to condition. So people might be experiencing a different kind of emotional experience, or might be more or less focused because of external reasons that do not necessarily impact the quality of the code in the end. So I agree with you. And I also have to say that whenever biometrics and all this kind of personal cognition or emotional related status come into the play, it is very hard to generalize. Still, this study showed that this kind of information might contribute to the performance of the classifier. So it could be interesting to replicate this study to see whether there is any possibility to develop a more robust and solid model, maybe involving more people to try to identify more features that generalize better than what we have observed, for example. So I agree with you that this needs further investigation, but this is still an indication that this could provide helpful information somehow.
Thank you.
Thank you.
How can you collect the data? For example, if I am typing, how do you know which piece of code I am editing?
We are just including the metrics about the behavioral and psychophysical metrics into the model without making any direct connection with the code, because the task was like very, we narrowed down the focus by simply assigning a given task. So they were contributing that piece of code, so they were not working on a project, they were just working on a task. So what we observed was certainly related to that specific part of the code, because this was what was observed as buggy or not buggy. So we're not working at the level of the project. But I agree, I mean, this will be also something that needs to be addressed if we want to scale up and to address this kind of problem in a more natural environment when people are working on bigger projects or they're contributing their code to a repository. Yeah.
Hello everyone, I'm Cui Ziyu from Institute of Software, Chinese Academy of Sciences. It's my honor to be here and talk about our work, detecting isolation bugs while transaction oracle construction. Database management systems such as MyCircle and PostgreSQL are widely used in many applications for efficiently storing and retrieving data. For convenience, we call database management systems as DBMS. DBMS treat the integrity of data as one of the most important promises and utilize transactions to ensure data integrity. For example, Alice wants to transfer money to Bob. The DBMS subtracts $100 from Alice's account and adds $100 to Bob's account. The DBMS utilizes transaction start statement and end statement to form a transaction and executes such a group of statements to ensure transfer data integrity. In DBMS, transactions are executed concurrently. DBMS utilizes isolation to ensure consistency of concurrent transaction execution. DBMS provides several common isolation levels to balance consistency and DBMS performance, such as read committed, repeatable read, and serializable in MyCircle. Isolation levels affect the visibility of transaction statements to other concurrent transactions. For example, at read committed, transaction 2 can see transaction 1's modification after transaction 1 commits. However, buggy transaction processing mechanisms and implementations can cause isolation bugs, which violate corresponding isolation semantics and lead to incorrect database states and query results. Here we show a real-world isolation bug which is detected by our tool at read committed in MyCircle. In this test case, two transactions execute concurrently on the init table. Red arrows show their execution order. Since transaction 2 tries to update the same row as transaction 1, it is blocked, and transaction 1 commits. Then transaction 2 is resumed and continues to execute the statements. After two transactions complete, we query the table and find that partial rows that satisfy the condition of transaction 2's update statement are not updated. Since transaction 2 updates the table after transaction 1 commits, we expect to obtain a database state shown in the left table, so this bug causes incorrect database state. Revealing such isolation bug is challenging, so we lack an oracle to judge whether the result of the actual transaction execution is correct. To address the challenge, we propose transaction oracle construction choke. Choke simulates concurrent transaction execution by decoupling transactions into independent statements and inferring their expected execution results. Note that we construct a transaction oracle without re-implementing a reference DBMS. For a decoupled statement, we construct its specific database view under the guidance of corresponding isolation semantics and the database change history. Then we execute the statement on its view to obtain its expected execution result. Statement database view determines what data the statement can see when it is executed. We construct statement database view based on the database change history. We first add a column row ID on the table. For a row in the table, we construct a list indexed by its row ID and add a node to record the row data in current version, set TS field as the transaction creating the version, and the deleted field as whether the row has been deleted. Similarly, other rows are recorded in the database change history. Statement's database view is decided by two factors, that is, the statement type and the isolation level of its transaction. We take an update statement and read committed as an example. The database change history contains the initial versions of table data. The statement reads all the latest versions in the database change history and constructs its database view as a table. Then we execute the update statement on its database view. To obtain the update rows, we construct a select statement with the same condition as the update statement and execute the select statement on the view. Finally, we update the database change history by attaching the versions of the two updated rows and setting TX field as TX1. For a select statement that is executed in the same transaction, it should see its own transaction's modification. It reads all the latest versions in the database change history and constructs its database view. We then execute the statement on its view and obtain its expected query result. The same process is followed for a delete statement in another transaction. We construct its database view and then execute it on its view. To record the deleted row, we update the database change history by attaching the version of deleted row and setting the TS field as TS2 and the deleted field as true. Based on statement's database view, we determine whether the statement is blocked. We perform a fine-grained row-based log analysis. For example, for a given update statement, we construct a query to obtain all row IDs that the statement accesses. We find that it accesses the first two rows. Similarly, a given delete statement accesses the last two rows. To determine whether two statements conflict, we perform the intersection. Since both statements accesses the row with row ID 2, we believe that a conflict has occurred. If the update statement executes before the delete statement will be blocked until the update statement's transaction commits. Finally, we compare transactions' actual execution result with inferred execution result by analyzing their statements one by one. We can detect isolation bugs which cause incorrect query result and incorrect final database state. To demonstrate the effectiveness of our tool Truck, we evaluate it on three widely used DBMS, MyCircle, MariaDB, and TiDB. MyCircle and MariaDB support 4 isolation levels, that is read uncommitted, read committed, repeatable read, and serializable, while TiDB supports read committed and repeatable read. In total, Choke has detected 12 unique bugs, among which 7 bugs have been verified as previously unknown bugs. Among the new confirmed bugs, 1 bug is fixed by DBMS developers. Here we show a simplified test case that triggers a new isolation bug in MariaDB at repeatable rate, which is detected by our tool Truck. In the test case, two transactions modify the init table concurrently. Red arrows show their execution order. After transaction 1 creates a snapshot at the first select statement, transaction 2 updates column C1 in the second row as 10 and commits. Transaction 1 then updates column C1 in all rows as 10. Then we query the table and find that transaction 1 retrieves only its part of updated rows. However, it should return all its updated data. So this bug caused incorrect query result. The developers explained that this bug exists in MariaDB for a long time. They mark this bug as critical, but they have not decided to fix it yet, since some applications based on MariaDB could be broken if the wrong behavior is fixed. In conclusion, we propose a general transaction testing approach, TROC, to automatically detect isolation bugs in database management systems. We construct a transaction oracle to infer the concurrent transactions' expected execution results without re-implementing a reference DBMS. The evaluation on real-world DBMS showed that TROC is effective in detecting isolation bugs. Our tool is available on GitHub. Thank you.
So do you know how those bugs is fixed? Is adding logs in the database can help?
Actually, we don't know what the root cause of these bugs, and also we don't know how they fixed.
But it's implementation bugs in DBMS, right?
Yes.
Okay, let's thank the speaker one more time. So now we move to the fifth talk, which is virtual. We were able to connect the speaker.
Hi everyone, I'm Sue, a PhD student from Texas A&M University. Thanks for attending my talk on small race. This is a joint work with Yifei, Rainer, Wilfred, Singh, and Professor Jeff Huang. So data race is a common problem in multi-threaded programming. It occurs when two or more threads in a single process access the same memory location concurrently without the sufficient protections, and also at least one of the accesses is writing. Due to the non-deterministic nature, data race often lead to unpredictable behavior and is notoriously difficult to reproduce and debug in production environments. The race detection problem has inspired a significant amount of research in different languages and platforms, such as the RacerD for Java and Thread Synthesizer for C++. Detecting data race for statically typed language is hard, and it is even harder for the dynamically typed languages, such as Smalltalk. As an early object-oriented programming language, Smalltalk continues to be used by many big companies in various industries with large legacy code base that require ongoing maintenance and development. A crucial problem in Smalltalk is data race. Smalltalk allows assigning any object to any variable without type restrictions, and allows forking new thread to execute arbitrary anonymous code block passed as objects. In Smalltalk, the data race can be introduced easily, but it is difficult to prevent at runtime. So let's take a look at a code example. In this example, each forcat message sent to a code block indicates the creation of a new thread. So in this case, we can see there are three different threads, the main thread T0, thread T1, and T2. Two data races are found in this example. The read on X in thread 1 can race with the write to X in the main thread T0. And also, the read on Y can race with the write to Y in thread T2. From this example, we can see three different challenges. First, as a dynamically typed language, variables are defined without initial types. Inferring types statically for all variables is challenging and computationally expensive. The second challenge is handling code block. A code block object can be cascaded, assigned to a variable, and parsed around in the program until eventually being evaluated. And this also brings us to the third challenge of variable use inside a code block. We also need to manage all the external variables and maintain the correct mapping between the variables and its memory location. So to tackle those challenges, we designed and built the first end-to-end static risk detector for Smalltalk. We proposed a novel approach to generate the LVMIR for dynamically typed languages and introduced the small IR for Smalltalk, which exclusively uses pointer to preserve all code semantic. Smalltalk employs threat-sensitive pointer analysis to perform the demand-driven type inference. It is fully automated and scales well to large code base. It has been evaluated on benchmark containing million lines of code and has revealed 37 real data rates confirmed by the developers. SmallRace is also open source and publicly available on GitHub. So let's take a closer look at how SmallRace works. SmallRace has two major components. The IR generator generates small IR from the source code, and the detector phase generates a data race report based on the small IR. To parse the Smalltalk source code, we define our grammar in Antler. Our grammar can successfully parse over 99% of the code base. Our Smalltalk AST is designed to capture all the semantic that is crucial for the risk detection. We translate AST into small IR instruction by instruction. We designed the small IR, a dialect of the LVMIR, to preserve all code semantic. A main technical challenge is that the standard LVMIR must have a type. To address this problem, our novel small IR represents type at the IR level as generic pointers, and models Smalltalk semantics with call instructions. Small IR can preserve all the Smalltalk code semantic into the IR, allows offloading the type inference as demand-driven in the analysis phase. The second key challenge is handling code block. We model a message being sent to a code block as anonymous function call. The pointers to the external variables used inside the code block are added to the function as signatures. So in the detection phase, we use a demand-driven type inference to reduce the workload by focusing only on the variable that requires the type assignments. To detect data race, we first utilize the interprocedural threat-sensitive pointer analysis to infer types for the pointer variables. We then extract the static threat trace, find shared variables, and perform risk detection using the hybrid happens before and log set analysis. So let's go back to our code example. We conduct threat-sensitive pointer analysis to resolve the point-to sets of each variable iteratively. Pointer analysis is a static analysis technique to derive the mapping between pointer and a variable or heap allocation. We iterate each statement, variable x and y in thread 0 point to memory location 01 and 02. And based on Anderson's pointer analysis, we add an edge on the constraint graph, indicating that T1 points to x in thread 1, and variable y in thread 2 can point to both T1 and T2, etc. With the block closure handling, we maintain the correct mapping between all the external variables used inside the code block. We demonstrate the feasibility of using pointer reasoning to statically improve the accuracy of type inference and polymorphism. Besides type inference, pointer analysis is also good for identifying shared objects. For example, identifying objects with different names but points to the same memory location. So to detect arrays, we analyze shared memory accesses by processing read and write events of each thread and organizing them based on their point-to sets for each shared memory accesses. As two memory accesses could have a happens before order, we also construct a happens before graph from the events currently stored in the program. We model two types of happens before constraints. First, within the same thread, all statements are happens before order. Second, for each thread creation, we also add a happens before edge from the fork event to the first event in the child thread. We'll conclude that there is a happens before order if two events can reach each other by traversing the happens before graph. So we will not report arrays if two events are happens before ordered. After filtering out all the false alarm with the happens before analysis, SmallRace also employs an event-driven log set algorithm to handle locking and synchronizations. So two data races will be reported by SmallRace. The first data race involves a read of local variable in local y in T0 and a write at T2. And the second race is related to the write to local x in T0 and a read in T1. We evaluated small arrays extensively with a large range of benchmarks that are executed concurrently for various applications, including 3 small talk tests extracted from the real application to medium-sized applications, as well as a large production code base. Small arrays analyzed over 1 million lines of code and have found tens of complex databases in the production code. We also collect the time consumption for the small IR generator, IRG, time for the pointer analysis, PTA, and the building thread trace, as well as the data risk detection. Small arrays took around 64 hours to finish analyzing all the benchmarks, on average of 200 seconds per KLOC. For each race report, we inspect the top 10 ranked data arrays. In total, small arrays detected about 400 arrays, and most of them are considered as either real arrays or mild arrays. A real race indicates that a race can lead to bad consequences in production and should be fixed immediately. And a mild race indicates that race is a valid race, but the consequence is benign. A common case for the mild race is the setter and getter race on Boolean variables, where the setter and getter can be invoked by the UI thread at any time. Small race does not offer soundness or completeness guarantee. It can introduce false positive, and it does not reason about branch condition. Also, our tools has false alarm due to the over-approximation of the pointer analysis and the trade-off between the efficiency and precision. So we have also received comments from our industrial partner for our risk finding in the memory monitor. So in this talk, we present the design and implementation of small arrays, the first end-to-end static risk detection framework for Smalltalk. Small arrays address several technical challenges in analyzing dynamically typed language feature using the demand-driven type inference and interprocedural thread-sensitive pointer analysis. This framework has demonstrated real value in an industrial setting. Our evaluation shows that small arrays is fast, precise, and scalable. It has discovered 37 real data arrays confirmed by developers. There is still room for improvements. The precision for the underlying data flow analysis and type inference can be further improved with the implementation of more language feature. We'll leave those as future work. Yeah, thank you all for your time, and I'll be happy to answer all your questions.
Okay, let's thank the speaker.
Okay, I'm Ed Geringer from NC State. I thought that was very interesting work. My question relates to your premise. You said data races are harder to detect in dynamically typed languages, and I hadn't heard that. I did a web search and didn't find it, and I asked ChatGPT, and it gave me a page and a half of stuff that I didn't think was any easier to understand than your statement initially. Can you give me a little example of why data races are harder to detect in dynamically typed languages?
Yeah, so this brings to our 3 challenges. If you look at the code example, I'm going to go back to this previous slides. So if you see from this example, they are, first of all, it's dynamic type. So the variable are defined without type annotation. For example, in this case, the X can be an object and it can be different types. And this variable can pass actually around different threads. For example, in this case, in thread 1, T1, actually there's an assignment from I can use a highlight pointer here. The T1 was kind of like has the same pointer set as variable X, so this basically points to the same memory location. So it means that the memory location can pass around inside the code block, inside a function, or even interprocedural. So making it very hard to resolve the actual mapping from the variable to actually memory location or the heap allocation. And the second challenge is actually the code block. In this case, you can see that this, for each forcat event sent to the code block, it indicates the creation of a new thread. And you can also see in this case that there are threads created inside another thread, so making this example even harder to be analyzed. That's why the data race is hard. And it's also very challenging because if you execute the same piece of code several times, you might get completely different results. So that is, for example, if you run a program maybe 100 times, and 99 of the time it gives you the result as 1, but there was one single time it gave you the results as 2. So how can you guarantee it's like safe to run this program in the production environments?
Well, thank you. I'd have to think about that, but thanks for your answer.
Yeah, thank you for your question. Yeah.
Given the dynamic nature of these languages, why are you focusing on static analysis instead of dynamic analysis?
Yeah, that's also a great question. But basically, the beautiful part of the static analysis is we do not have all the runtime environment for our code base. So we do not, with the static analysis, we can just parse the source code and do all the analysis offline without you need to setting up the environment, configuring all the configurations, setting up the server, etc.
So I see this technique can be easily applied to other dynamic typed language like Python, for example. Is that correct?
We're more targeting for the Python. Yeah, for sure. There are like some inherent challenges that can use our framework as long as we develop like the similar front end, and then we can basically, as long as the framework can generate LLM-IR, and then we can reuse basically most of the part in our backend.
Yeah, so for Smalltalk, there is not many analysis infrastructure. That's why you convert Smalltalk to LLVM-IR, right?
Yeah, that's exactly why we are trying to generalize our approach in order to facilitate analysis for other programming languages, or we're trying to generalize those challenges that we can be adapted to a lot of future works.
Okay, thanks.
Yeah, thanks for the question.
Now we move to the last talk of the session.
Yeah, thank you. So my name is Hongyu Zhang. I'm going to talk about CONA, which is about diagnosing batch failures for cloud systems. So our work is slightly different from the previous talks. Yeah, so this work is mainly done at Microsoft Research Asia. Okay, so about the background, we all know that nowadays there are a lot of complex and large-scale software systems, like Google and so on, Bing, right? So they are online service systems. So their reliability, availability is very important, it's very crucial. So when incidents happens, we need to diagnose the large-scale software system, locate the faults, and fix the problem. So that's very challenging for complex systems. Okay, as a motivating example, for example, we try to deploy a new version of Microsoft Exchange service. So this service will be executed on many nodes. Yeah, some nodes forms a group called AG, availability group. Yeah, basically, it's a cluster of nodes for the tolerance purpose. And many VGs may form a large cluster, And for a large and complex system like a Microsoft Exchange, there are many versions of the system, many versions of the service system. Then if we deploy a new version, we don't know if an incident happens, whether this incident is caused by the new version, the bugs in the new version, or caused by some transient problems, some temporary problems like a network unstable or user errors and so on. So we try to find out whether this problem is actually caused by the version we deployed or by some transient problems. Okay, so engineers need to debug the problem when the incident happens, right? So they may encounter data like this. So there are some multi-dimensional data, for example, APP, which has many values, and versions, there are different versions like V1, V2, V3, and so on. Different AG groups, these are availability groups, different cluster numbers, even different data centers, and so on. So there are a lot of data, multi-dimensional data, right? So developers need to figure out what really happens, what could be the root cause. So they may look at the version number, for example. In this case, for a simple heuristic like a version, so the developers may look at the distribution of the failures across different versions. Then in this case, they may find that version 2 is the root cause, because version 2 contains most of the failures. But in fact, this simple heuristic may lead to some false positives and false negatives, right? Because the problems may be due to a combination of the attributes. For example, when you run app2 on the version 2 service, then the problem happens. If you use other app versions, if you deploy the system on some other versions, then the problem will not happen. So basically, here we try to find out a combination of a certain attribute values, which lead to the root cause. So that's the challenge. So we have a lot of attributes. We have a lot of attributes, and each attribute may have many values, right? Many values. And then we try to search for a combination that is responsible for the incident. There are also some background noise, background data. So the system always have some transient failures, some user errors, and so on. So there are always a lot of background failures. But if a certain attribute value combination is triggered, then there will be a lot of failures, much more than the number of background failures. So actually, we found that this problem is not unique for Microsoft Exchange. Actually, this problem is a kind of a common problem for many systems. For example, for this VM unexpected reboot failure. So if the hard disk is on hard disk fails, then the VM will be automatically reboot. So the developers may ask, the question, is this incident caused by a storage problem or computing node problem or some networking problem, right? So there are also a lot of attributes, multi-dimensional attributes. Each attribute may have many values. So developer also try to look for the responsible attribute value combination that causes a lot of failures. The number of failures is much more than the number of background noises. Right. So the current process is still about rule-based method. So, for example, developer look at one attribute and then locate the fault. But the rule-based method has very low coverage. For example, it only identifies 14 out of 835 incidents. So actually, it's not very effective. And also, current method requires a lot of human effort. They have to manually look at the spreadsheets, look at the data, and try to figure out what the possible root cause, which attribute combination actually is responsible for the sudden increase of failures. So it's very time-consuming. Yes. So there are also many other instances of this kind of problem. For example, node failure. The computing nodes, like the computing server, failed. Then what could be the root cause? So people may look at the logs. There are some passing logs. There are some failing logs. So developers also need to manually analyze the logs and compare the passing logs with the failing logs, and then try to debug the problem. So we see that there is a common pattern. We call it batch failures. Batch failures. So basically, failures that affect a batch of instances of the same subject. So for example, the failures of a node, the failures of a service, and so on. So This failure affects many instances of the same subject, and each failure instance has a collection of attributes that describe the context where the problem happens. Attributes, and also each attribute has many values. So our goal is to locate a certain combination of attribute value pairs that is responsible for the incident. And also there are some background noise, background data, and we also have a target data, right? So we need to compare the background data with the target data and try to debug the problem, locate the incident. So we call this kind of problem as the problem of diagnosing batch failures. Batch failures. Okay, so we propose this tool called Conan, which is a framework for batch failure diagnosis. So basically, we collect the data, right? Collect data, the incident data, and there are also all kinds of metric data. Then we do some data transformation to convert various input data into a unified data format. Then we develop a simple meta-heuristic search-based method to identify the attribute value combination, the pattern, that maximum the user-specified objective function. Try to locate that attribute pair. Then after that, we do consolidation. We try to reduce the number of results being found and return the results to the developers. Developers then can look at the diagnosis report and identify the problem of the system. We also call this attribute value pair contrast pattern. Contrast pattern. So basically, that's the set of this attribute value pair that is responsible for the incidents. So we have many of these kind of pairs in the background class. We also have this responsible pair of attribute value combination in target class. So our goal is to search for a large space of attribute value combinations to locate that contrast pattern, which is actually the responsible attribute value pair. For example, in this case, the target class has this pair, then we can identify that one, and then we can locate the root cause. Okay, so in order to locate these contrast pairs, we propose a simple search-based method, which is a simple meta-heuristic method for solving this kind of combinatorial optimization problem. So we use two simple operators, add and delete, right? And we also define a certain objective function. And for different problems, this objective function could be different. And then we also define the expected returned number of patterns. Then we do search. So this is actually a simple meta-heuristic search framework. Okay, so then after we obtain some candidate patterns, we do this consolidation. Basically, there are some redundancies among the returned results. For example, APP value, the value of APP is APP1, the value of version attribute is V1, and the other pattern is version is V1, right? So then in this case, we could reduce the number of returned patterns. We could consolidate them. So the reduced pattern is only P1, only P1, not P2. P2, if we just return P2, then many false positives will be returned to the developers. So the P1 is the actual result we are looking at. Right, so as the example, so here for the Microsoft Exchange problem, so we define objective function like this. So basically, it tries to compute the difference between the number of patterns in the target class and the number of patterns in the background class. We try to maximize this difference in our search. Yeah. So we try to search for the pattern that maximize the objective function. Yeah, maximize the objective function. So that's a simple local search problem. So here for the example, right? So for example, version 2, app, version 2, and so on. So we identify top 3 possible candidates. Then we do pattern consolidation. Yeah, pattern consolidation. Then we only return this app2 v2 as the contrast pattern to the result to the user, yeah, to the developers. So that's the final result. And developer could identify the system problem based on our returned results. Okay, yeah, so we have applied the Core9 in practice. It has been successfully integrated into many products in Microsoft, like Azure and Microsoft 365. And in the last 12 months, it has helped developers diagnose more than 50 incidents from 9 scenarios. And it saved the developers' time and stopped many incidents from impacting more users. Now, there are some real success stories, so I won't go to details. So if you are interested in it, you can look at our papers. So basically, we have applied it to real-world practice and have some success stories. Okay, so basically in this talk, we introduced the design, implementation, and practical applications of Core9, which is a framework for diagnosing batch failures of large-scale software systems. So Core9 has already been integrated into many real-world products and has already saved engineers time and effort. Okay, so that's all from me. Yeah, thank you very much.
I have actually two questions. One about what kind of meta heuristic do you use? Is it an exact method, or is it like meta heuristic to approach the solution, like genetic algorithms?
Right, that's the simple meta heuristic method. That's a simple search method. So we define 2 operators, add and delete. Then we also define an objective function. Then we randomly pick one, add one value into the set, and then we try to add the other one based on the objective function. Yeah.
But what is it an exact technique, or is it a technique that calculates the approximate solution?
That's it's not the exact value.
Exactly. Yeah. So if you use an approximate technique, so a technique that approximates the solution. I've seen in your in the results that the function have more or less near values. So how can you be sure that the solution that you found is the one that you have to address, or you have to
Yeah, so this is a search method, so it may not return the optimal value all the time. But according to our study, it can identify most of the patterns we want. Yeah. Okay. But it may not identify all the problems, all the patterns.
Okay. Thank you very much.
For the attributes, you collect through logs?
Collected from system monitoring data. Yeah, there's some monitoring framework which monitor the execution of the large-scale systems. So they will, some monitoring framework. Yeah.
Okay, thanks.
Okay. Thanks for your talk. I have a question. I'm interested in using the Core9 tool for self-deployment. I think this paper is split the group like the background group and the treaty group.
Sure.
Yeah. However, if the deployment is completed, and the failure is happen after the complete the deployment, like the memory leak. It made happen after the deployment. How can we split these two groups to find the root cause?
Right. So for the deployment, this is just one application of code9, right?
Yeah.
So there are many versions in the system. So version is an attribute. But if we don't consider deployment issue, we can consider other issues. Then we have other attributes. But still the same, right? Other attributes, we still have many values. We still need to identify that particular combination that is responsible for the incident. Right? But the attribute could be different. It may not be the version attribute. It could be some other kinds of attributes.
Yeah, okay. Thank you.
Yeah, thank you.
Thank you for your presentation. And I have a question about the search algorithm. Could the search algorithm be replaced by an end-to-end approach such as a machine learning or deep learning model?
Yes, I think that's a very good question. I believe some fancy machine learning algorithms like deep reinforcement learning could also play a role here. Yeah. So many other search algorithms like evolution algorithm, PSO could be also applied here. So here we just use a simple meta-heuristic search algorithm.
Will the strategy of the search will influence the performance?
Right. So here we just want to make it faster and more efficient. But some time-consuming algorithms like evolutionary algorithm may also work here.
Yeah. Thank you.
Okay, let's thank speaker one more time.
Yeah, thank you.